I'm going to talk about power amplifiers for 5G and phased array MIMO applications in VSS, the AWR system simulator. Just figure out how to change slides. So just as a background, our love affair with our phones are continuing, and 5G is round the corner, and it's promising kind of massive increases in capacity. So they're talking about 1,000 times increase in network capacity. How are we going to get 1,000 times increase? Well, there's going to be more spectrum for one thing, sort of 10x on spectrum. There are going to be a lot more and smaller cells. Again, that's going to give us a 10x performance increase over 4G. And then the subject of my talk is where the other factor of 10 comes from, and that's the high directivity antennas, smart antennas, and MIMO technologies mandatory within the specification. So I'm going to look at the kind of ecosystem of linking power amplifiers to highly directive antennas and the challenges that will bring about in the design space. There's also other things to consider with the power amplifier, things like DPD and envelope tracking to try and improve the efficiency of the power amplifiers. Before we go up to system level, I'd like to talk a little bit about the circuit level tools, because if you consider something like a phased array, it's a tight-knit problem between the power amplifier and the changes of impedance that occur as you scan the phased array. So we've developed a capability where it's possible to run the circuit simulator in situ with the EM results. I mean, effectively, the antenna is just a set of S parameters as far as we're concerned for the circuit simulator. We're electronically steering the array, so we only need the set of S parameters once, and then we can run that together with the circuit simulator and look at the effect of so-called active impedance effects on the amplifier. And then moving up to system level, the capability there is to take the results that have been generated from the field solver, so we've got the far field pattern of the array, and to be able to bring that up to system level in a single model that we can then steer, but still maintain the interactions with the power amplifier. So I'll give you some examples of this as we go through. The other side of the characterization is to include the effects of TR modules. So, you know, in the center of the phased array, you're probably going to be pushing more power into those amplifiers. There is a possibility of compression and memory effects. And so we want to look at the effect of hardware impairments in the overall system when we look at the phased array and the drive-in amplifiers. So in situ antenna and circuit analysis, we use EM to characterize the physical structure of the antenna, and that will return us with a set of M-port S parameters. We may have multiple feeds. In MIMO, we're going to have subarrays being driven by different information streams, and there could be other things like polarization diversity. And all this is really nice. It's a set of S parameters, but there is a problem in that when we want to steer the array electronically, we put in a phase vector into the array, and what's going to happen is that the return loss from one element will be coupled with all the others at the same frequency, but the phases will be either constructive or destructive, and you could actually get more return loss than you're putting in. So you could blow your amplifiers up, worst case, because you've got huge resonant structure with lots of coupling between the elements. So it's important to be able to characterize those effects to understand, you know, what kind of effect it's going to have when your amplifiers are changing as the array is steered. I mean, one way to think about this is to look at the situation if you had a couple of antennas. You could stick it on a network analyzer and you could measure S21. That's the coupling between two antennas. But the real case is you've got multiple antennas, each one coupling to every one other. Depending on the geometry, the closest ones will couple most, but all of these will change in phase as we drive the array electronically. So the net result of that is you can probably see there's a circle, a magenta circle on there, which will be an isolated patch as we scan it in frequency. And we've also got the gain circles superimposed on that plot. Now, when you start to couple the array elements, instead of sitting at a single point at bore site, these elements, because of the coupling and impedance changes, they move around. and there'll be static points at bore site. But as you start to tune the array electronically, these things will spiral around, and that's the load that we present to the amplifier. So this is the result of the active impedance, and it's important to realise that the low pull effects will then change the gain of the amplifiers. So the coupling between the antenna elements is an M-port network, and that contains all the information we need to understand what the effects will be. The isolated antenna plus the S parameters due to the coupling gives us the complete picture. So it will cause various effects. At cancellation points, there will be what's so-called scan blindness at certain angles, and the coupling between those elements will influence the impedance that we see at the ports. So when we do in situ circuit simulation together with EM, if we've got a load-sensitive PA model, we can capture those low pull effects, and we can see the effect on the far field pattern as we actually steer the array electronically. All this can be done at circuit level, and you only need to run the EM simulation once to extract the S parameters. We then can go on to look at things like resonances in the feed network, resonances due to coupling, and do things like optimize the feed. So I'll go through a real quick example. This is one of the examples that ships with Microwave Office, and it's a 16-patch phased array driven by 16 amplifiers. We'll talk about different architectures later on where you might have different numbers of amplifiers compared to the number of elements in the phased array. Things like hybrid RF, for example. So we've got S parameters coming from the EM simulator. The feed network is simulated using conventional passive elements, and then we have an amplifier with its active components there on the right. Now in the past, if you did these separately, you'd probably do some EM simulation, get the S parameters, and then excite the ports with ideal loads to look at the far field. But then you then need to check whether the load you're seeing will actually affect your amplifiers. And you had to go around the loop several times to get to a point where the design was stable. So it's basically the old story of iterate, iterate, iterate. And that's what we've tried to remove with this in-circuit simulation. So what we can do now is simply in the field solver, solve for the S parameters, extract that data. We only need to do that once. And that completely characterizes the load for any excitation that we might, any steering angle. All we need is the S parameters. So it's just once with the EM. This next slide shows the corporate feed from the circuit simulator. There's a bunch of splitters and some phase shifters. In this case, they're done with equations to keep things simple. And then within these sub-circuits, each one of those TR modules contains a mimic amplifier, the phase shifter, and an attenuator, which we can control with equations as we scan the phased array. Just a close-up of the mimic amplifier we used. Again, this is a standard example if you wanted to open it up later and take a look. So then effectively, when we run the co-simulation, we specify harmonic balance as the circuit simulator, and we couple it to the EM simulator through this fill form. So the EM structure will then be run together with harmonic balance. The co-simulation will do the complete phased array. And then effectively, you can tune the phase shift, the steering vectors, and watch the phased array change, and look at different beam angles and the like. You can do optimization, various other things can be done. Anything you can do in circuit simulation could be applied at this point. So in this first section, I just wanted to talk about the circuit level capability, where it's possible to look at these low pull effects, couple it to EM simulation. And now I want to move the discussion more towards the system side of things. And I will also talk about some of the new capabilities we have for phased array in V14, which has just been released. So within VSS, what we're trying to do is provide a single model that can take all the data you may have measured or got from circuit simulation, put that into a single model which is very flexible and includes all of these effects. In other words, VSS will also handle coupling effects and active impedance effects, so you can investigate the effects of load pull, but this time at system level. I'll just let the graphics run through. So the sort of things we can do with VSS is investigate different architectures. You can have arbitrary location of your individual patch antennas, for example. So you might want to reduce side lobe levels by having a nonlinear distribution of the points, or you could use a gain taper. We can add the RF links characterization. We can take an architecture of a TR module and extract a file for that in both frequency and power to characterize the drive to the phased array. And because we can include the mutual coupling and S11 of the individual antenna elements, we will also be able to simulate the active impedance of the phased array. So there's a simple element and a fill form. You won't be able to read this, I guess, unless you've got very good eyesight. But you can read in radiation patterns and set the steering angles and various other things. It's possible to set up user-defined gain tapers, user-defined geometry of the phased array, very simply. And here's a couple of examples. Once that phased array has been defined, we can scan it in any cut and look at the theta-phi antenna patterns. Now you can start to play around with it. We can look at things like element failure analysis. So you might have a random distribution of failed elements, or pick some specific elements, switch them off or have them soft fail, and see what effect that has on the overall system response. You can see the side lobes are starting to come up in this example. In terms of characterizing the RF links, what we can do is specify an architecture for the TR module, and we can start an automatic characterization which scans it in frequency and phase and power and writes that to a file. And then at the bottom there, you can see that we can link that to the phased array in a configuration file. So it will use those TR module definitions as part of the simulation. So it's a very efficient way of representing the system. In terms of coupling, there's kind of two ways you can work here. You can, on the top there, we see an array that's been subdivided into edges, corners, and the center. So if we're looking in the center, everything kind of looks the same in all directions until you get to the edge. So we could characterize a pre-coupled array in EM by taking a point and putting the geometry of the other points around it, terminating all the surrounding ones at 50 ohms, and then making a measurement. That will give us a pre-distorted patch response that's taken into account all the coupling. That will be one way. And we'd need to take three test measurements from EM, one for the corners, one for the edges, and one for the middle patches. And we could then read that into our model in VSS and have an accurately defined model that includes the effect of coupling on the field of the antenna. Now the second method is we take a non-coupled patch, but we measure the complete phased array in EM. If it's possible to do that, we can then take the coupling matrix from EM and pass that to the system simulator. So that will give us not only the distorted, due to coupling, the distorted field of the antenna, but it will also have the active impedance results because we have that in the coupling matrix. So it depends on the geometry, what's possible to be solved in EM as to which approach you take there. Obviously, the bigger the problem is going to come to a point where it's going to be too costly in time to actually run the EM solver. And then once we have the data, we can call up the different measurements we've made in EM, put the patches into the geometry that we have, and then we can do some trade-offs, look at the effects of isotropic versus coupled patches, and we can see the effect that would have on the overall gain and the pattern of the phased array. So once you've run an EM simulation, such as the one on the left there, it will auto-generate a data file, which is the theta-phi 3D radiation pattern of the particular patch, and that can be read by VSS. So the flow would kind of be set up your geometry in the EM simulator, run the field solver and look at the far field, and then once you're happy with that, export that patch response through to VSS, associate it with the phased array model, and we should then be able to reproduce the shape of the phased array. So there's a nice flow there. It's also possible to kind of go back the other way. So if you've designed a phased array in VSS and you have access to the taper, the gain tapers, and also the positions of the blocks, if you then have a primitive element defined in terms of a layout geometry, maybe that's one patch at the bottom there, then those dimensions can be sent across via a script to Axiom, the field solver, and it will set up the geometries so the phased array is then available for you to run a simulation on in EM. So that's kind of a top-down link. And this shows taking a primitive patch and then sending it out as a phased array where the geometries were predefined in the system simulator. So these are done by scripts that we ship with the software. Okay, so I'd like to return a bit more to the active impedance and the way to simulate this and look at the effects that it generates. So again, this is just basically showing our different TR modules, and all of these are simulated at the same frequency but with different phasing as the array is steered. And then we're seeing that S parameter coupling matrix means that all of those will add constructively or destructively at each port. So you could get an unexpected amount of S11 occurring that's hitting your amplifier through load pull. So the left trace are the coupled patches with a bore site. They're just single points. But as I said, when you steer the array electronically, these things will spiral around and move in perhaps unexpected ways. So how do we get the data to simulate active impedance into our system simulation? Well, there's a number of ways using behavioural models. We've obviously sat through the previous talk, and there's a nice ecosystem there with the AMCAD tools, which can take data from measurement or from simulation and include memory effects and load pull. Another way is we can generate from the circuit simulator, in this case, the example I showed you earlier, we can extract AM to AM and AM to PM as a function of gamma. Okay, so we can map the AM to PM model to different gamma points, and then we can present that to the system simulator, or we can map gamma to steering angle, and then have a model where when we sweep the steering angle, it uses the appropriate AM to AM, AM to PM model. So you will see the load pull effects due to that. So that can be automated with a script. So here we see on the left a model at bore site, which is the AM to AM and AM to PM for each individual element. And then on the right side, these are unique models that have been mapped for each scan angle. So a file-based model is one possible way if you're happy with using AM to AM, AM to PM. There's no memory, obviously, in that case. There are other behavioural models available, obviously X parameters, or load pull, vector load pull based models, where we exercise the model in a circuit simulator, do the normal kind of gamma thing, do the load pull with the gain circles, and then that model can be used together with an architecture in VSS. There's also a behavioural model in VSS called TDNN, which stands for Time Domain Neural Network. And we can extract from a circuit simulation a behavioural model that will include memory. And the simulation here is showing those models being exercised with a block that has short-term memory effects. And in the top trace, it's a little hard to see, we're comparing three different cases. One is the TDNN model, which includes the short-term memory. The one at the top is a circuit co-simulation using circuit envelope. So that's a dynamic simulation which is run in the circuit simulator with IQ data. So that will include the memory effects also. And the middle, as a reference, is a memoryless model. So what we can actually see at the top is the model without memory has symmetrical sidebands. The two models that include memory have asymmetry in the sidebands. And furthermore, we have a model in VSS that can handle algorithms for DPDs. So we've added a DPD to that, which may be important in certain phased array applications. And you can see that it's brought down the side lobes, but because of the memory effects, it's not quite as effective, or it's a more accurate representation than the memoryless model can provide. So there's some interesting simulations that can be done there at system level. So everybody in the room here, I think, saw Tony's slides on AMCAD, and he described that in a lot of detail, so I won't add too much more to that, except to say that we're working together to look at different architectures for phased arrays, including load pool, so there should be some interesting things coming out of that collaboration. And the interesting thing here is the ecosystem, where you can link in models from test equipment and then generate a macro model that can be dropped effectively into VSS, as you see in these slides here. So I won't say too much. The nice thing is that the mismatch effects, short-term, long-term memory, can be included, and you pick the level of model that you need for a particular job. So that's going to be interesting to work on. Now I want to talk about some of the new capabilities in VSS v14. First of all, we're looking at different types of beamforming systems that are going to be used in 5G. One of the things that's going to be important, I think, is to take into account the space and cost limitations that we're going to, because of these high frequencies, you can't bolt a whole load of amplifiers to the head end. There's going to be space and heat problems. So typically people are looking at some kind of hybrid designs where you use a combination of digital beamforming and analog beamforming to reduce the number of amplifiers that you need. You might have less amplifiers than the number of elements in the phased array. So within VSS in V14, we're exploring a number of these architectures, and we've included the capability to have a bus inside VSS. So instead of a single line, we can have a bus of N amplifiers with a single amplifier representation that then goes straight into a phased array, making it very easy for you to generate quite complex architectures with very little effort. So the idea here with hybrid beamforming is you might have a MIMO structure with a number of input streams. You can't, the maximum number of streams will be limited by the number of amplifiers you have, but here we might have N amplifiers, but many more antennas. So you would have subarrays being driven for each portion of the MIMO. You then need to match that beam to the complex channel and form the optimal beamforming weights. I'm not sure if this slide comes across very well, but this is an example we have for hybrid beamforming, and the idea is we have in this case, four information channels. We then go into a matrix where the digital beamforming weights are generated. I actually generated those in MATLAB and ported them across. Then I have a bus, so that amplifier in the middle are actually four amplifiers on a bus, so these are the four MIMO streams. Coming into the phased array, we have a 4x16 matrix for the analog beamforming, and then the phased array has 16 elements in the output. Perhaps I should have brought that up first, it's a bit easier to see. So you can see the various blocks of that defined. So this next slide shows the signal processing. V14, the matrix multipliers is a new element in VSS, so it's been a great help in being able to do this matrix math very efficiently. But essentially, the weights here were calculated as a steering vector. We take the channel H and we calculate the steering vectors for that to get the optimal beamforming weights. And there's a split that's set up. There's various ways in algorithms you can do this. But essentially, the analog beamforming steers the angle very broadly, and the digital beamforming would be, in a typical system, would be used to reduce interference due to unwanted signals. So it's actually possible, if you link to something like MATLAB, that you could close the loop on this, and you could have a dynamic channel for MIMO, generate the beamforming weights, pass that back through MATLAB to our blocks, and you could update the beamformer based on some kind of interference. So these are things I'll be working on and looking at over the coming months. Yeah, and that's just showing the link that we have with MATLAB. MATLAB co-simulation is actually really useful in VSS. You can pass a matrix of data to MATLAB and bring that back in a single hit. So it's actually quite efficient, and it's a good way of implementing algorithms for control loops. The last thing I really want to speak about is the new phased array generator. We've got a lot of feedback from customers that they wanted something to make it easy to set up the phased array. This will let you specify the geometry. There's a kind of fill form. You can see visually what's happening. Go through and set up the feed, the number of elements, and the antennas. And the most requested thing is it's got a 3D viewer. So you can see what's happening with the array as you design that. Once you've been through and designed the array, you can set up for MIMO or single feed. You can press a button and it will export the design straight into VSS, where you can run an analysis on it. You can also do things like failure analysis directly there in the wizard. So there's some of the new features in V14, the sort of matrix support, the bus support, and also this phased array wizard, making it much easier for you to generate designs for phased arrays. So that concludes my talk. Hopefully I've shown you how you can design phased arrays. It's going to be very important for 5G. We can look at the effects of coupling on the overall system response, and also things like load pull due to active impedance. So that's all I have. Thank you.